Okay, so welcome back. Let's finally start what I consider a very important topic in the subject. And for today, actually, we will not really be talking about stable homotopy theory. We will sort of do the unstable case. Instead of infinite loop spaces, today we will be talking essentially of single loop spaces. But you will see this is doing actually most of the work for the actual theorem about spectra that we will see next time. So let me recall I defined, so if T is a finite totally ordered set, I defined the gap T, and this is just the set of pairs T prime such that T is less than T prime and there doesn't exist anything in the middle. It's just perhaps just a notational convention. And let me actually put a remark that was implicit in what I said last time, but I forgot to say. Gap T has a canonical order. So we have T prime is less than S prime, essentially if T is less than S. And the way you should think of this is, suppose T is, I don't know, this set here. Gap is really the set of the minus, the lesser or equal sign in this thing. And it has clearly a canonical order. Sort of seeing the gaps between objects, that's where the name's coming from. And in particular, for every T prime in gap, we got a map 1 to T, which I called GTT prime. Maybe I should have called it chi T prime actually, but doesn't matter. GTT prime is just, well, it's just the obvious map you can define by picking the one simplex that witnesses exactly this gap. Okay, this is just a small bit of combinatorial trickery. Oh, and let me say that Gi minus 1I is defined to be Gi for brevity when T is this set N. So, okay, definition. So let C be an infinity category with all finite products. Then an associative monoid is a functor and from delta up into C such that for every T in delta, I have a map from M of T to the product of M1 for all T prime in gap. This is just the product of M of GTT prime. And we ask, is an equivalence. Okay, this was the definition I gave. And last time I sort of messed up trying to motivate this definition. Let me try to do the proof properly this time. Oh, just a small bit of terminology. Associative monoid in space, in the infinity category space of spaces, is called an E1 space. And the one is because this thing is related to the configuration points on the one-dimensional line, the configuration space of points. So the configuration of points in R are essentially just given by the order of the points, and you can do a higher dimensional version, but we will not consider it, unfortunately, in this class for lack of time. Okay. Questions so far? So far it was just a definition. So actually, let me give you what is perhaps a more familiar definition. So
could you just repeat what you said about the higher dimensional version that we won't consider?
Oh, there is. So this. We will see today a recognition principle for loop spaces. So for spaces of the form loops X, and there is also a recognition theorem for spaces of the form loops N of X, which is related to the configuration spaces of points in R to the N. And that was just to say why there is an E1 here. And there is actually a notion of En for n greater than 1. But okay, as I said, we won't talk about it.
Okay, thank you.
I also have a short question. Is this so? They are also these Siegel spaces, which have a somewhat similar definition.
We will see them in a second. They will be what I call E-infinity spaces or commutative monoids.
Okay, but
well, no, okay, we will see them actually Monday probably, not in a second. But yeah, that's not a coincidence. The definition is similar. In fact, there is a similar definition for En spaces for every n, but as I said, I'm not going to talk about it, unfortunately. But I put some references in the notes. Actually, no, not in the version currently, but I'm going to upload them. So if you want to learn this story more in depth with a lot more details and a lot more examples, I literally put links to books that you can explore to your heart's content. So, okay, but let me give a definition. Let's see be a category. Now that's just a normal category. Let me call them a classical monoid. Is a triple a category with finite products. Forgot. A map from the terminal object into M, and a map mu from M times M into M, such that mu is associative and unital, by which I mean mu composed with eta, comma, the identity. Oh, sorry, I'm writing it for the identity. Mu composed with eta is the identity on M, that's unitality. So let me write it. And new identity. And that's associativity. And okay, I actually didn't define what maps of monoids and of classical monoids are, but okay, maps of monoids just mean natural transformations of such functors. And maps of classical monoids, so map of classical monoid is f from M to M prime that respects the unit such that this and the multiplication. So sorry, mu prime f comma f is f composed. Yeah. This is just if you want f of x times y is f of x times f of y. Okay, this is probably the definition you've seen before. In sets, it's just a classical notion of an associative monoid. And okay, the first results I want to talk today is that if C is a one category, there's an equivalence from monoids and classical monoids. And the equivalence is actually kind of easy. Let me, okay, other questions about this? No, okay. So actually, let me describe how this goes. Let me put.
Excuse me.
Yes.
In the definition above, did you mean infinity category or?
No. Here I mean category. Here
Okay.
I need a one category.
Okay, thanks. Sorry.
Oh, you're right. Sometimes I put a one, sometimes I don't. That's a leftover of what we call seminar conventions in, well, where I did my PhD. Yeah, there is a whole story. I probably shouldn't say it on record, but catch me up when we're not recorded, and I might say some more stuff. Okay. Okay, from sketch, I mean, I will just give you functors going in both direction, and I'll leave to you to verify that the compositions are the identity. So let me first give actually the hardest functor. So if M is a classical monoid and T is a finite totally ordered set, we can define mu T from M to the T into M as follows. So mu of the empty set, it's M. And by empty, I mean just the product of T copies of M in the order given by the ordering of T. So that's just the terminal object into M, and that's just eta. And then mu T is mu of, let's see in which order am I doing it. The identity of M, mu T minus the maximum of T. So if you want, morally, this is mu x1, sorry, x0, xn is x0, xn. Motivation. And so, for example, you can see that mu of 0 is just the identity of mu of 1 is just mu, etc. And the associativity tells us that it doesn't really matter in which way I'm splitting. So associativity tells essentially that mu T union S with lexicographic order, where TS has the lexicographic order, and essentially this functor delta op into C is just encoding this mu T for every T. That's the intuition you should have. So, okay, let me define then. So suppose M is a classical monoid in C. Let me define a functor. Yeah, actually, no, before I do that, sorry, I need a small piece of notation. So suppose I have a map in delta, and TT prime is a gap in T. I'm going to define f of TT prime is a subset of S. Sorry, of gap S. And this is the set of all gaps that lie between f of t and f of t prime. So for example, if I have the map 1 to 2, sending 0 to 0 and 1 to 2, f of 0, 1 is just the set 0, 1, 1, 2. So you imagine the gap spread and covers just a set of gaps in S. I have my gap TT prime. So this is T, this is S. this is f of t prime. That's just a piece of notation. That's going to be convenient. And okay, now if I have a classical monoid, I can construct a functor from delta up to C as follows. So on objects, it does what you have to do. Just take the product of T copies of M. And if I have a map, I have to send it to a map in the opposite direction. So from M of S to M of T. Oh, sorry, not M of T, M of gap T. That's the thing that's forced to you by the Siegel conditions, by this product condition. And how does it work? Well, you can think of these, the gaps of S split as the union over the gaps of T of the image. So you can think of these as the product over the gaps of T of M of F T T prime. And this goes to the product over the gaps of T of M. And here I'm just taking this mu F T T prime. So I'm doing essentially the obvious thing. If you unwrap what it is the only sensible thing to do. You have all the objects that all the points of M corresponding to objects in a fiber get multiplied together with the order given by the fact that are in T. And I'll leave you as an exercise to you to verify that this actually satisfies the conditions. And it's a functor and etc. The associativity forces it to be a functor. So this gives a functor. Mon classical C to mon C. And to go in the opposite direction is actually easy. Once you've seen these, you send M, a functor from delta up to C. You need to send a tripole. So how do you do that? Well, the underlying object has to be M brackets 1, if it has to be the inverse of this. And then the unit is going to be the composite of the canonical equivalence of M0, the canonical isomorphism, sorry, we're in one category, of M of 0 with the point. It's the case T equals 0 of the condition. And then M of, let me call it G0, which is perhaps a bad name. By G0, I mean the unique map from 1 to 0. And mu, I need a map from M of 1 times M of 1 to M of 1. Well, first I take the inverse of this map G1, G2, which is an isomorphism by the hypothesis of 2. And then I take M of, what did I call it? Oh, I didn't give it a name. Okay, let me call it M of H. Where H is exactly this map that I described before, sending 0 to 0 and 1 to 2. So the two gaps of 2 get collapsed in one gap of 1. And so that's implementing the inverse. And you have to check that this is indeed associative and unital and etc. But that's just a diagrammatic argument in delta. And this gives this gives the inverse. And you have to verify the two maps. It's obvious that in one direction it's the same, and in the other it follows from these Siegel conditions. Is it clear? So this is the reason why we need this more complicated definition in infinity categorical world is because, for example, look at the definition of classical things. Here I'm asking you to have equality between maps. That's problematic in infinity categorical world. What you have to give are homotopies between map, and then you need compatibility with these homotopies that include even higher homotopies and etc. And if you look at what this delta op is giving you, it's giving you exactly that. If you unwrap what a functor means, it's giving you exactly those compositions. And that's a very convenient way of putting it. Okay, questions about this? No. Okay, let me give you an example that's not a monoid in sets. Oh no, first actually remark. So pi0 from space to set preserves products. So pi0 of, so if M is an E1 space, it is a monoid in spaces, pi0 of M is a monoid in sets. Just because with the canonical, with the obvious multiplication and everything that's given by the previous isomorphism. And so we say M is group-like, or an E1 group if pi0 of M is a group. There are a bunch of equivalent ways of phrasing this definition, but that's all that I'm that's the definition I want to take for now. And that's a correct notion of non-commutative group in this infinity categorical setting. Okay, this definition works only for spaces, but there is in fact a way of making it work for arbitrary infinity categories. Actually, this might be an exercise. It's probably going to be an exercise. Yeah, actually, let me state it as an exercise. An E1 space is an E1 group if and only if the map, so M of 1 times M of 1 goes to M of 1. Actually, it's, well, okay. M of 1 given by, morally, I'm going to write it in symbols, so it's clear what I mean. X, xy is an equivalence. And really, the way to say this is in fact secretly the map from M of 2 to M of 1 times M of 1 that's induced by G1 comma H. Sorry, MG1 comma MH in the notation as before. H is this map that encodes the multiplication, and G1 is the map that encodes the first projection. But okay. Let me put this in exercise. And this definition clearly works in every infinity category with finite products. You can copy it. But okay. Questions? Because it's time to give an important example of E1 groups. So, example. So let me write like this. Let X be a pointed space. Then omega X has a canonical E1 group structure given by concatenation of loops. Oof, cannot write. I'm going to define it, but okay, that's. And in fact, the main theorem of today is that this is going to be the only example of E1 groups. Every E1 groups is going to be of this form. And okay, how do we construct this? I need to construct a functor from delta up into space. And oops, sorry. The functor is going to go like this. It's going to be the limit delta xt, where is just the category where I take the objects of t and I add a cone point. And there are no maps between the objects of t. And xt is just this diagram here, where for every object of t I have a point, and at the cone point I have x. And this map is just inclusion of the base point. So let's see what happens. So when t is 0, I'm taking the limit of this diagram here. And this category has an initial object. So all that I get is 0, is the point. I take t equals 1. I'm taking the limit of this thing here. And we know that this is exactly the loop space of X. So let's see what happens for t equals 2. So we have the limit of this thing here. Now there are various ways of computing this limit. But possibly, let me write what I think is the most geometric way. There is a purely diagrammatic way as well, but let me do. So these are maps in pointed spaces. You can realize these as maps in pointed spaces, and you can bring the limit inside. So you get the co-limit of, sorry, S note into X. And the point is that this co-limit has a completely geometric description. This is just 2 points with, well, in this case, 3 arrows like this. And let me say marked with a base point, say downstairs. You can do the same argument that we did last semester to describe the homotopy push out, for example. And you get this, and this is equivalent to S1 wedge S1, just by, I don't know, collapsing the middle element. And so this is just maps S1x times maps S1x. That's omega x times omega x, as we wanted. And in fact, you can see that the multiplication map, which corresponds to restricting along these, oh, maybe I should use a different color. Restricting along this exterior thing, discarding the 1. So these are labeled by the elements of T, so it will go by 0, 1, and 2. Discarding the 1 corresponds exactly to the composition of loops. Under this homeomorphism, this gives you exactly the map from S1 to S1 wedge S1, and that's the composition of loops. And okay, for Tn is the same. You just get one of these things with n things. And so in particular, pi 0 of omega x is just pi 1 of x with a group composition operation, and we know that this is a group. This is, I don't know, choose your favorite proof that this is a group. That's so in upshot, we have a functor from pointed spaces to E1 spaces. Sorry, groups. I'm going to denote with this group upstairs, the subcategory of groups. Let me write it. And the theorem will be, well, we'll say many things, but among those things there will be that this is an equivalence when restricted to connected pointed spaces. Okay. Questions? No. Okay. So what am I going to do? Oh, okay, I'm going to define, in fact, the goal is going to define the adjoint of this omega. We want an inverse. Well, let's start by finding an adjoint. And it's a very important functor, so it deserves a name. So let M be a monoid in spaces. Its classifying space Bm is just the colimit of M seen as a functor. So Bm colimit and it is pointed by the canonical map. M of 0, which is the point inside the colimit. You know, every value of M has a canonical map into the colimit. So this gives us a canonical base point. Okay, a couple of words about why this is called classifying space. remark. When M is, well, let's say, comes from a nice topological group, and I'm not going to say what I mean by nice. Lie group is enough, but you can do a bunch of things. And then comes a nice topological group. There's a G. There's an equivalence. Sorry, there is a bijection of homotopy classes of maps from X to G and isoclasses of principal G bundle on X. And if you don't know what a principal G bundle is, ignore this. It's just to tell you where the name comes from. And actually the proof follows the line, the same strategy as exercise 2 in the last exercise sheet. Well, at least one proof. There are others, but the one that's more natural at this point. The reason I'm not saying more is that I would have to introduce what principal G bundles are and trivialization and etc. But if you've seen principal G bundles, you can probably fill in the gaps. There are some non-trivial arguments here, but it's well, you can actually, if you Google for it, you can actually find a Mathreflow answer I wrote a couple of years ago with all the details. So I don't think it's lying too much. And anyway, and if you haven't seen what a principal G bundle is, just ignore that. It's just trying to explain where the name classifying space is coming from. We're actually going to use it for vector bundles in a while, but yeah, let me not say more. Other questions? No.
So if this G is a nice topological group, does this BG in our sense comes from the BG in the topological sense some way?
What is BG in the topological sense? I mean, if you look at Milnor's construction of BG in his original paper, and you look at the formula I gave you for geometric realization a couple of weeks ago, you get exactly Milnor's formula. I mean, this definition
Okay,
is exact.
great. That was the question.
There are a couple of different models in the geometric setting that are proven to be equivalent, but if you choose the right one, it's literally given by this formula.
Okay, great. Thanks.
Okay. Good. So B now is a functor from monoids and spaces to pointed spaces. And my goal is to say that this is actually the left adjoint to omega. So it doesn't want to show it's the left joint to omega. So in order to do that, I'm going to need to give you a unit and co-unit of this adjunction. So the first thing is that if M is a monoid in spaces, I have a natural map from M to loops of B of M. At the level of underlying spaces, it's kind of obvious what to do. You have M of 1, the underlying space of M, and these maps to M of 0 via, say, m of d0 and via m of d1, and this maps to this co-limit. And this diagram commutes by the property of the co-limit. This is a fragment of the co-limit diagram. And these are points, and these are points. And so we get a map m of 1 into omega bm. But okay, and the same strategy actually works to give you a map of E1 spaces. Now the idea is, so we have this co-limit diagram, delta op cone into spaces, that sends n to m of n and infinity, the cone point, to bm. That's just a co-limit diagram. And we can find a fragment here by taking for every t, I have a map from t cone to delta op, to that, sorry. I'm doing it wrong. Sorry, when I defined it earlier. No, never mind. I have a map from this guy to delta that sends t just to 0. The cone point, let me call this minus infinity to t. And the unique map, like this, goes to the inclusion of t. Like, I mean, this might look complicated, but it's just, you know, parameterizing all the different inclusions of the points into t. And this gives me, oh yeah. So putting all this together, this gives me a map into spaces. So what am I calling this? I'm not calling this. So let me call this D. D op. So concretely what I have is, I have m of t mapping to m of 0, 1 for each point in t, and mapping to bn, which is just by the inclusion of the co-limit. And this is just m of the inclusion of t in t. And this just gives me a map, natural transformation, to this omega bm of t, since this omega bn of t is the limit of this fragment here of the diagram. I mean, I'm just saying that composition of loops is compatible with the multiplication in M, if you want. So this gives a map M to omega bm space.
Sorry, I'm a little confused by your notation with the cones. So why is it, when you define d, why was it minus infinity? Because the maps go to the...
Yeah, sorry, let me call it infinity. It's just that then I'm going to apply it to the op, and then that right cone point will become a left cone point.
Okay, yes, and then in the line below, I missed the op, and then the cone goes in the other direction.
Yeah.
Okay.
Maybe introducing this separately is more confusing. This diagram hopefully is perhaps clear already what it does. It's for every point of t, it's seeing the inclusion of 0 into t that picks up that little point. And all of these includes into b of n, which is the colimit. Okay, so that's actually the most important map. Let me define the other guy. The other guy is really much simpler. Sorry, omega x into x. So remember, this is just the colimit of the limit of diagrams like this. This is b omega x. But we can write it as the colimit of the limits of diagram like this. I put the identities. Here instead, and that's just x. Sorry, it's not equal, it receives a map. Because there is always, for example, in the case. And here you have to be a bit careful because these maps are all non-homotopic. At every finite stage, this map is non-homotopic, but the diagram is not. The magic is, so for example, you get a map from omega x to x that just sends, if you want, every loop to gamma of -1, for example, after you make a bunch of choices to identify what it does. So this is for the case t equals 1. But this is, of course, homotopic to the constant map because you can always slide along a half circle. The point is that you cannot find such a homotopy coherently in delta. And so in the end, the map is not non-homotopic. This is another example where you can find a bunch of non-homotopic maps and take the colimit, and the colimit is not non-homotopic anymore because the diagram was not non-homotopic. It's kind of a subtle point, and it's not really needed to understand the proof, but it might confuse you. It certainly confused me yesterday evening when I realized it. And I said, wait, why do we have null homotopic maps? This map is not supposed to be null homotopic. So I thought it was worth mentioning. Okay. So lemma, actually, let me give a name to these maps. This is going to be the co-unit, so let me call it epsilon. And this map here is the unit, so I'm going to call it eta. So epsilon and eta satisfy the triangular identities for a junction. Concretely, this means that I have Bn goes to B omega Bn, and this is Bn. This goes to Bn via B epsilon of n, and this is going to be the identity, and that's the other one. Oh, sorry, x. And okay, I'm going to verify on the first. The other works analogously. So, okay, what is this? So this is the colimit for n delta up of m of n, and this maps to the colimit for n in delta up of the limit of this diagram of, well, n plus 1 copies of the point, and then this maps to Bm. And this goes to the colimit of the up of the limit of the constant diagram at Bm. And you want to say that this is homotopic to the identity. That when you unwrap this, this is just colimit delta up to m of n to the colimit delta up to Bm, where this is just a colimit of the inclusions of mn into the colimit. And this is the identity by definition. And this is, if you want, this is just the this map. And okay, I probably never said that, but the geometricalization of the nerve of this category is just contractible, which are already implicitly used in the definition of epsilon. So I'm not getting anything interesting. And again, this is another example of this fact that you have null homotopic maps and you get a non-null homotopic map in the colimit, because for every n, the map from mn to Bm is null homotopic, but the colimit is the identity, so it's very far from null homotopic. It's kind of strange, but well, that's why we shouldn't forget about the higher coherences. They do play a role. Okay. Questions about this? Okay, then let me state the recognition theorem for loop spaces. There's a theorem, and maybe I should say some names here. That's definitely Boardman-Vogt, proved it for the first time. The first proof in print, I think, was due to Peter May. And I'm going to follow the proof in Seagal's paper, Cats and Cohomologies. Peter May uses a different approach. It boils down to essentially the same ideas, but I don't want to say what operats are, so I won't use this language. So let M be an E1 space and X a pointed space. First, the map eta is an equivalence if and only if M is an E1 group. And this statement is actually the most important one. That's the one from which all the others will follow formally. 2, Bm is connected. And 3, epsilon from B omega x into x, and this can be explicitly described is equivalent to the inclusion of the connected component of the base point. And we know that we cannot hope for more because omega x cannot know more than the connected component of the base point. Because you're moving through paths, so you really cannot see more than that. But this is telling you that you can see everything. These paths. So in particular, epsilon is an equivalence if and only if x is connected. And therefore, the adjunction B f adjoint to omega restricts to an equivalence between pointed connected spaces and E1 groups in spaces. That's because when M is a group and X is a connected spaces, in this case, the unit and co-unit restricts to equivalences. So this gives you inverse equivalences. Okay. We have half an hour. I think I can do the proof of this theorem, hopefully. In half an hour, but first, other questions about the statement? No. Okay. Oh, and actually, let me put a corollary here that says that the functor sending m to omega bm is the left adjoint to the inclusion. Space group inside non-space, non-linear spaces. And it's called group completion. It's sometimes written MGP for this reason. So if you want, it's formally inverting all elements of M, morally. So that's just an immediate consequence from the theorem. Okay, and now is the moment where we need to use some fact about the category of spaces that I haven't mentioned yet. And it's the proof of this theorem essentially boils down to the descent property for counits in spaces, which I'm going to state and say maybe a couple of words about why you would expect this to be true, but I'm not going to prove. There is a reference, however, in the notes already now. So we put a different theorem. Descent property for colimits. And okay, that's perhaps not the most intuitive way of phrasing it, this property, but it is the way we will use it. So actually, sorry, I need a definition before stating this descent property. So let me say definition. So you have FG from I to C, two diagrams, and alpha, a natural transformation. we say alpha is Cartesian. Let me move this. If for every arrow ij in I, the square f of I, f of j, g of I, g of j. So this is alpha I, this is alpha j, this is f I goes to j. Well, okay, these are the r's. Is a pullback square. Okay.
So here C is an ordinary category.
No, here C is an infinity category, sorry. I mean, you can take it for an ordinary category, but the only ordinary category to have the property I'm about to state is going to be the zero category. So that's not going to be very interesting. In fact, this is part of topos theory, if you know topos theory, but I'm not going to mention topoi ever again. So just if you know this is part of that circle of ideas. So okay, the descent property of colimits says the following. So let I be a small category. Fg from the cone on I into space two diagrams, and alpha from F to G a natural transformation such that alpha restricted to I is Cartesian. Then, suppose also that G is a colimit diagram. Then alpha is Cartesian if and only if F is a colimit diagram. So in particular, if I have a Cartesian natural transformation, what I'm going to, in particular, which is the statement that we're going to use, colimit of F times colimit of Gi, colimit of G, sorry, Gi is F of I. And that's if alpha is a natural transformation. And okay, I think I have to tell you a couple of things of where this is coming from. This crazy property and why it's called descent. So the first remark is via categorical reformulations, which are not hard, but just a bit tedious. This property is equivalent to space over colimit G is equivalent to the limit over I of spaces over Gi. So giving a space to the map to the colimit is equivalent to give a space over each Gi in a compatible way. That's just, you need to understand how the limit is done in categories and wrap a little bit, and essentially you get the statement above. It's a bit tedious, but it's not really hard. At least it's not hard if you do it in exactly the right way, as often it is the case in category theory. And so this also goes off in the name colimits have the Van Kampen property. And so what this has to do exactly with the Van Kampen theorem would take a while to unwrap, but there is a way of. But the idea is you can glue stuff over subspaces. So, and then this follows immediately from the straightening, unstraightening theorem, which I never even stated, but okay, the theorem allows you to rephrase it as this. This thing, as this statement is saying that a space over X is the same thing as a functor from X to spaces. And okay, the straightening theorem is definitely a major theorem that I'm not going to even try to hint how you prove it. And I don't even want to state it precisely. But the idea is that giving a functor from X into spaces is the same thing as giving a space over X. And the functor sends every point of X to its fiber. We have seen a very baby version of this last semester, constructing the covering spaces for functors into sets and building a covering space into from that. And okay, and that's all I want to say about the proof of the descent property. Probably those of you that have already seen this, understood this, and those who haven't. So I'm not sure how helpful this remark was, but anyway, the key point is that if alpha is a Cartesian transformation, you get these equivalents here. And that's true in spaces. It's not true in spectra, it's not true in pointed spaces, it's not true in abelian groups, it's not true wherever. This is it's true, to be precise, this is true in every infinity topos, for those of you who know what an infinity topos is. And the only example you know so far are spaces. So it's really a very specific property. Okay.
Is there any way to see why is it not true in pointed spaces?
I mean, take your favorite example and it will fail, actually. I mean, you can see because in the colimit in pointed spaces, you are collapsing all the base points in the colimit to the same base point, right? That's how you compute the colimits in the pointed spaces. And that's what breaks this property.
Okay.
Oh, actually, no, I have a simple example, actually. You can take the empty category in pointed spaces, and the colimit in pointed spaces, and let's say, no, that's not what I mean. Oh, okay, sorry, I don't have an example off the top of my head.
Okay.
But you can do a very simple example with, I don't know, push out is definitely enough. Probably a coproduct. No, a coproduct is enough, actually. This breaks the fact that coproducts are disjoint. This property implies that coproducts are disjoint. That is that this map is a pullback square. That's an example of this property when I is a 2-point category. And F is, for example, descent. So if this is the case, I is a 2-point category and F is, sending this to A. Well, okay. Okay, let me not try to reconstruct this on the flight. But anyway, this is false in pointed spaces, as you know.
Okay, great, thank you.
Yeah. Okay. Good. I'll need another lemma, technical lemma, to prove the theorem. Actually, I'm probably going to be able only to prove the first part of the theorem, but that's okay, because that's the important part. We're going to see how to get the rest. So the other lemma is, suppose you have a simplicial space, or actually a simplicial object in every category. Then there's an equivalence to y0 and the colimit over n of yn plus 1, where I say n plus 1 as n with a point added at the end. This is what's called, this is a variant of the so-called extra degeneracy argument. Essentially, we have some additional maps on the diagrams on the right, coming by the fact that we can, well, y has some extra functoriality, and this allows us to construct a homotopy back to y of 0. And in particular, this means that the colimit on the right exists. So I have no hypothesis on the category C. But we're going to use it for spaces, so it's going to be kind of not very important in this particular application. And okay, so the idea is you take delta plus 1. This is the category of finite non-empty totally ordered sets and maps and monotone maps preserving the maximum. So there's a subcategory of delta, has all objects, but I'm taking only the maps that preserve the maximum. And so the first remark is that this inclusion, delta plus infinity inside delta, has a, which direction does it go? Has a left adjoint, which just adds a maximum. And okay, so in particular, this left adjoint, since it's a left adjoint, is co-initial. So what this boils down to is that this colimit for t in delta op of y of t union plus infinity is equivalent to the colimit in t in delta plus infinity op of y of t. But now this category has a terminal object, 0. And so this is just 0. It's a small trickery. If you want just a small trickery, these additional maps allow us to retract everything. These actually, if you unwrap what it means for a concrete map in spaces, say, this is the so-called spaghetti homotopy. This allows you have essentially a space of paths, and you say the space of paths is equivalent to the space of starting points because you can retract the path back to the starting point. We have seen something like that in doing something with the homotopy fibrations, I think, last semester. A similar argument. If you unwrap what this adjoint is doing, it's doing exactly that. It's taking a simplex and retracting it to this distinguished maximal object back. But okay, that's more to give intuition. The proof is just a formal trickery. Also, you shouldn't eat spaghetti like that. Really, you shouldn't. But you should learn how to use a fork. But okay, that's a different thing. Okay, so let me actually, we have 15 minutes. I think that's enough to do the main step of the theorem. There's part one of the theorem that says that, so if M is a monoid in spaces, then eta from M to omega Bm is an equivalence if and only if M is an E1 group. That's actually really where the main point goes. Okay, everyone good so far? Good. So first proof, well, if eta is an equivalence, pi 0 eta is an isomorphism from pi 0 of M and pi 1 of Bm, so M is a group. Okay, this was the silly direction, but we have also to do the silly directions from time to time. So the real content is the other direction. It's the case when M is a group, that this map is an equivalence. To do that, note, do the other direction. Note that eta can be checked to be an equivalence on underlying spaces. Because a map in a functor category is an equivalence if and only if it's an equivalence on all values. It's an equivalence pointwise. But we have, if you remember back when we define it, I have that the value of M on any point is determined by the value on M on 1. And so it's enough to check after evaluating on 1. So what this boils down to, so we need to check that this diagram that I wrote before D0, yeah, D0, D0, I think it's D0, is Cartesian. That's what it boils down to. Remember, this was the map on underlying spaces from M of 1 to omega B of M. And we're going to use descent. Now you understand why the fact that certain maps coincide is. So to do so, let us introduce an auxiliary simplicial space. And so this is just the one we already saw, P of M going to since N to M of M n plus 1, seen as N with an additional point. And actually, let me think 1 second if I'm doing this right. D1, yes, okay, I'm doing this right. It's just that I have to swap D1 and D0. It's not really important, but just making sure that the diagrams are correct. So this comes with a map to M induced by the inclusion M inside M. And we claim if M is a group, so let me call this alpha. Alpha is Cartesian. That's the claim. And let me show you how this finishes. With this claim, we're done. Because then by descent, this is Cartesian. And now, well, this is M1, and this map is exactly D1, if I'm not mistaken. And by the lemma, extra degeneracy argument, this is M0, and if you unwrap this, should be exactly D0. And this is Bm. And that's the property we needed. So we just need to prove that alpha is Cartesian. Okay, so what does this mean? So let f from M to M map in delta. We need to show that Pm of M goes to Pm of N.
Excuse me, where did you define alpha?
Oh, sorry. Alpha is the map induced by this inclusion.
Okay, thank you.
Sorry, I can, so okay, let me stop on a second and let you stare at this page. So you have this M, which is just PM, which is just the adding a base point. Essentially, I am and I mean, maybe it makes sense. So sorry. And okay, I'm going to give you the formal proof in a second. But let me first see what happens when M is a discrete, and M is discrete, what this map is doing. So this is M1, M plus 1, and this map just discards the last coordinate. Is M1, M prime 1, M prime, M plus 1, M prime 1, M prime, N. And what this map is doing whatever it does on the first coordinate, but on the last coordinate, it's taking the product of F inverse the product of all M for all I greater than F of N, Mi. And so it's clear that in order for this to be a pullback, we have to be able to divide. Because you want to reconstruct M plus 1 from from m prime m prime n plus 1, which is from this product and these elements here. So concretely, let's actually first reduce to the case where n is 0, to where maybe it's clearer. So I can write n as the disjoint union of n minus 1 and n. And m as the disjoint union of where do I want to go? Fn minus 1 and Fn blah 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 n with the lexicographic order. And so I can split this square as n minus 1 times m, and sorry, that's not what I mean. I mean Fn minus 1 times m Fn n plus 1. This goes to Fn minus 1 times m Fn m. This goes to m n times m n plus 1. Sorry. No, n minus 1 plus 1 n minus 1 times f m of n. So I can see this as the product of two squares, one corresponding to n minus 1 and one corresponding to just n. And so by induction, I can decompose this square as the product of two squares. So by induction, I can assume n is 0, because then I do the decomposition for n minus 1, etc., etc. So I have essentially I have a map f from 0 to m, which corresponds to some I in 0m. And now what do I have? I have I m n plus 1. Sorry, I have, oh, that's not what I mean. So sorry, let me start from downstairs because that's easier. So in this case, I have m of 0. No, I have, yeah, m of 0, m of n. Here I have m of 1. And here I have m of n plus 1. And I want to say that this is Cartesian. Sorry, I'm over time. But that's a point. So in the end, to say that this is Cartesian, this boils down to say Am I doing this right? I hope I'm doing this right. I think I am messing up some indices. But in the end, this map should be, so you can identify this m plus 1, m of 1 to the m, and this map corresponds to the map that, if you allow me to write it diagrammatically, sorry, x1, x m plus 1, this goes to x1, xm, and then puts the product. And as in the exercise, by induction on M, we see this is an equivalence for M if M is a group. I am regretting choosing little n as a symbol for the indices now, but sorry about that. I should have used I and J. Because you go by induction and you show that the multiplying, in the end, you can reduce to the case when m is 1. So it's enough to show that this map is an equivalence. And this finishes the proof of this part. You can see that in the end, you after a bunch of reductions and inductions and etc., this Cartesianness boils down just to these, and then you apply descent, and the results magically pops out somehow. Okay. Okay, next time, consequences of these, and we move to commutative monoids and spectra. Let's finish the proof with the two easy steps afterwards, and then commutative monoid and then spectra.
Excuse me, could you quickly scroll up a bit? I missed this sentence. Yes, this one. What does it say? No, a little bit down. Yeah. Right from the diagram, what does it say? I want to say this is?
This is Cartesian.
Ah, okay, thanks.
That's sorry, yeah, that's terribly written. Apologies. But okay, that's essentially the first step. You reduce the case n equals 0, and then you reduce to the case m equals 1 by induction, by seeing what the maps are. And then m equals 1 is exactly the statement that m is that big M is a group. So, I mean, there is this mysterious descent statement that makes things work. I don't really have an intuition about why it should work, except that it looks very reasonable. But it does. Okay. And I mean, this reduction to the case n equals 1, m equals 1, n equals 0 is easy. Sorry, I went a bit fast, but it's, if you write down what the maps are, it's fairly clear, for example, that this square here decomposes a product of smaller squares. And so you can check it only for those squares. And I actually throw away a bunch of squares that are just identities everywhere, because those are not interesting. Those are obviously Cartesian. And then you just see that the formula is given by that map, where you want to reconstruct the last element by the product of all elements and all the previous ones. And this is clearly some kind of group condition. The details take a little more to formalize, but anyway, this proof is already in the notes in full detail, I think. You can see that the square corresponds to the first factor, has equivalences on the vertical arrows are equivalences, so are identities actually even, so it's not. Okay, let me stop the recording if there are no more questions.